For this problem, we are tasked to solve the moment about the coordinate axis. To do so, we need to break down the resultant force into its individual components acting in the x, y, and z direction. So first things first, let's set up the coordinates for the head and tail of the vectors. Going from the origin, A here has coordinates of positive 6 units in the x direction, 0 in the y direction because it has no vertical shift, and 4 units in the z direction. So in summary, that is 6, 0, 4. For B, going from the origin, it has coordinates of positive 2 in the x direction and positive 3 in the y direction and no movement in the z direction. And so that is 2, 3, 0. Next, we will apply ratio and proportion to get the components of this force vector. But to do so, we need the length of the force vector AB and the length of its component. So by using head to tail method, we can get the component by finding the difference between the head and the tail of the vector. So L sub of x, that is equal to 2 minus 6. Or we're just basically subtracting the x component of B, which is the head, to the x component of A, which is the tail. That's equal to -4. And for Ly, we just subtract the y components of B to A. That's equal to 3 minus 0. And for Lz, that is equal to 0 minus 4, which is equal to -4. Now, we can apply the Pythagorean theorem in 3D so we can get the diagonal distance from point A to point B. So the overall length, that is equal to the square root of L sub x squared plus L sub y squared plus L sub z squared. Plugging in the values, we get square root of -4 squared plus 3 squared plus -4 squared. We should get approximately 6.4 meters. Now applying ratio and proportion, we can solve for the component of the force vector. So getting the ratio of the component to the overall length, we get f sub x over f is equal to L sub x over L. Manipulating this equation, we should get f sub of x is equal to f times L sub of x over L. Doing the same to the other component, f sub y is equal to f times L sub y over L. And f sub z is equal to f times L sub z over L. And then we substitute the values. Since we only care about the magnitude first, let's disregard the sign of these lengths. So force is 200 kilonewtons times 4 over 6.4. That is equal to 125. And since Fz is just equal to Fx, therefore we should get the same result. And for Fy, that is 200 kilonewton times 3 over 6.4. That is equal to 93.75 kilonewton. Now that we have our components, before we go on solving for the moment, I want to talk about sign conventions. So first, let's talk about the right-hand rule. So the right-hand rule is a simple way to determine the sign of a moment in 3D. So first step is you point your thumb along the axis of interest and curl your other fingers. And if your fingers curl in the direction of rotation, then that moment is positive, and if not, it's negative. And that's basically it. Now to solve for the moment about the x, notice that only Fy could induce a rotation about the x-axis, because f sub x is parallel along the x-axis and f sub z touches the x-axis, which means they both have no perpendicular or moment arm distances to induce a rotation. So m sub x is equal to f sub y times 4 meters. That is equal to 93.75 kilonewton times 4 meters, which is equal to 375 kilonewton meters. Now the sign for this should be negative, because if you try to apply the right hand rule along x, the moment is opposite in direction. And that is our final answer for the moment along x. Now for m sub y, only x and z would induce a rotation along the y-axis. So for the sign convention, I'll let you analyze this by yourself. This should be positive fx times 6 meters minus fz times 4 meters. My is equal to 125 kilonewton times 6 meters minus fz, that is 125 kilonewton times 4 meters. So my is equal to 250 kilonewton meter. Now for mz, only Fy can induce a moment along the z-axis. So mz is equal to Fy times 6 meters. That is equal to 93.75 kilonewton times 6. We get 562.5 kilonewton meters. So these are our final answers.